on to shape some. Let's talk about conformations and configurations. If I draw these three structures up there, are those different molecules?
No problem.
Are they different molecules?
No.
What happens in this case is that what we believe happens is that carbon atoms don't necessarily have totally free movement, but around these sigma bonds there is some sort of ability to rotate and move. So like a slithering snake, these things are not just sitting there rigid in one conformation, but they can actually sit there and twist and turn, and they can assume different conformations that may look like a different molecule to you, but it's the exact same molecule, just in a different conformation. So these are different conformations of the same molecule. There, that's a different conformation of the same molecule. So all of these just represent different conformations of the same molecule. Now, what happens if I change this just slightly? Let's change it slightly. Are these different molecules, or are they different conformations of the same molecule? Now, why are these different molecules in this case? There's some sort of structural difference between these. It doesn't involve just rotating. In other words, no matter how much I rotate this thing, will this ever become this? No. There's no conformation that this can assume that will make it into this. The only way I can get this into this is to do what? To break a bond and stick it someplace else. That is a configurational change. I've changed its configuration. Okay? It's no longer a conformational change, it's a different configuration. It still has the same chemical formula, which is interesting. So we still have the same chemical formula with a different configuration, so this is now known as an isomer. And we call this a very special type of isomer. It's called a constitutional isomer or structural isomer. It's different in structure. It's a structural isomer, also called a constitutional isomer. The number of isomers increases with the number of carbons, and it is not just a linear relationship. As the number of carbons increases to 10, it is a logarithmic curve that jumps, and you get a huge number of possible isomers. I want you to figure out all of the possible isomers for a C6 hydrocarbon, just hydrogen and carbon. You can do that at home, you don't need to do it right now. I want you to figure out all of the constitutional isomers, and they have to be different from each other for a C6 hydrocarbon.
With any number of hydrogens?
C6 would have how many?
Well, yeah, 6 carbons, but
It
how
can't
many
be-
with
the only
any
thing
number
is
of
I don't want it to be
hydrogens?
cyclic. It can't be cyclic. It has to be what we call an open chain. So open chain. It can have branches, so forth, but it can have C6. Anytime you have what is called a saturated hydrocarbon, these hydrocarbons, you'll have a C6H18. Okay, it follows the formula C to the N, H to the 2N plus 2. So I want you to figure out all of the constitutional isomers for C6H14. Okay? Now, if I take and say that this is one of the possible isomers. So I say, okay, that's one of my isomers. This is known as the straight chain form, or also called the normal chain. So this one just the N or normal chain. The one thing you'll notice, if I take this and I make it into a cyclic structure, is the cyclic structure even a possible constitutional isomer of the normal chain,
No.
C6?
You don't have enough hydrogens.
I have few hydrogens, why? Right, I had to get rid of two hydrogens in order to close the chain structure. I had to get rid of something in order to bring the two carbons together. So this has a different chemical formula, so it is not a constitutional isomer of a normal chain C6H14. Is this a constitutional isomer of something else? What if I put this? Yeah, I'll move it just a second. Let me just filter right here. Are these constitutional isomers or structural isomers? They look completely different, don't they? Should we count how many hydrogens this has? What is the chemical formula of this thing right here? 1, 2, 3, 4, 5, 6. This one has 6. So this is a C6, this is a C6. This one has how many hydrogens? 12. How many hydrogens does this one have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Do I put any more hydrogens off of that one? No. So this is, well, these two are constitutional isomers of each other. Even though they have very different structures, they are structural isomers. All right. When we go into the configurations, we also notice configurations are due to what is known as impaired movement in the molecule. Anytime I can take a structure and form a double bond in it, I now have hindered rotation. That double bond seems to lock this thing into one conformation that we would call a configuration now. So this is kind of a locked situation. Because of the presence of the double bond, it's locked. That means that a group on this side is different than this side. Okay? The only way I can get this group on the same side as this side is not through free rotation, but through what? Break a bond and reform it. And so these represent two different configurations of the same molecule.
Is that just breaking the pi bond only?
Yeah, I didn't break the, well, there's another way to do this. I could break the pi bond, spin it, and then reform the pi bond. So there are two ways. Or I can physically break the sigma, move it over, and so forth. So it doesn't matter. But we have to break a bond in order to get it from one position to another, right? That's the only way. We can't just twist the thing and get it into the other configuration, right? So these represent two different configurations. This one, we say that these are on the same side, so I use the Latin term for same, which is cis. Okay? On the other configuration, this one, where they're on opposite sides, it's like going across the ocean, transatlantic flight, right? This is a trans situation where they're on opposite corners.
So you have a transit side?
They're in the corners. So trans are on opposite corners, cis are on the same side. So cis, same side, trans, opposite side. And it doesn't have to be a simple group, it could be a more complex group, which is I can have this now, where I have this carbon atom with its hydrogens, this carbon atom with its hydrogens, and I have a double bond here in the middle. This would represent where this group down here and this group up here are on opposite sides. This represents a trans molecule, whereas if I break this and move it over, this represents a cis configuration. Okay? We talked about what happens in the first events that take place in about 1 picosecond, 10 to the minus 12 seconds. When a photon of light hits this bond in your eye, there is a pigment there that's known as 11-cis retinal, that the bond is broken. It now leaves the sigma bond. The molecule rotates out of the cis configuration and reforms a double bond in the trans configuration, and this converts light energy into mechanical energy. So I can't reform this bond because of the limitation of holes, but atoms don't have holes that you plug things in, right? Okay. So everyone understand that configuration changes. These are also known as geometric isomers. Space and trans are geometric isomers. They are more highly related than just a constitutional or structural isomer. They are very, very closely related in all of their physical and chemical properties. The only difference is where these are absolutely located in space around that hindered rotation. So this takes place anytime I have hindered rotation in a molecule. So what happens when I have, I'm breaking all my molecules apart into pieces. What happens if I take this guy right here and I put it back together like that? Do I now have hindered rotation in this structure?
Yes.
Yes. I now have hindered rotation. It can move a little bit, but I have hindered rotation in terms of free movement. So in this case with these cyclic structures, we could also have geometric isomers. So we'll talk about this later on where we get geometric isomers with these cyclic structures because of hindered rotation. Alright. Last thing I wanted to talk about was bond polarity today. And bond polarity becomes really important not in terms of the calculations of what the absolute charges are on an atom. They become more important as we look at how molecules behave in an entire solution. Okay? If we look at bond polarity, you can take a molecule, and there's one in the book where we can use an example of this right there ready for me that I use. Okay. This one right here. If I take C, minus, plus, we'll just go R right now. If we want to know what the absolute charge, remember somebody asked me, okay, these are resonance formal charges, but if we look at the other resonance structure, which is this structure, and the hybrid, let's do the hybrid, we only put a partial negative out here, a partial positive out here, and an R, right? As we looked at the resonance hybrid. Okay. And somebody asked me, do we know what these absolute values are? We have a pretty good idea as to what they are. And that idea comes from an equation, and the equation is a simple equation. So mu is equal to 4.8 times delta, I believe, or sigma. I get my notation that I use in the book right. It's the electron charge, delta, and then the other is d. D is the diameter between the two charges. So what is the distance between these two atoms right here, okay, between their nuclei? And then their electrons are involved with this. This is a simplified equation that puts this unit into what's known as a debye. Okay. The debye is a coulomb per meter charge, so it's an absolute charge. And it tells us something about the absolute charges. If we simplify it into this equation right here, this debye, this distance now, instead of becoming a meter, we can now calculate it in terms of angstroms rather than a meter. It makes it a lot easier because most of the atom distances are measured in angstroms. An angstrom is 10 to the minus 10 meters. Okay? And this becomes our electronic charge, or the charge distribution between these two. So if we look at this now and we say, okay, what is our other resonance form of this? It's this guy right here. So we're saying, okay, between these two, which of these predominate? And we can make some reasoning as to which one predominates based upon the octet rule, right? Saying this. But can we prove that with absolute charges? Okay? And so we have to have some numbers here. It says that the C double bond O distance is about 2.4 angstroms. Okay? Oh, sorry, 1.23 angstroms. I'm looking at this wrong. It's 1.23 angstroms. The overall bond polarity is about 2.4 Debye. Trying to go too fast here. 2.4 D. Okay. Now they're saying, what is the overall charge distribution in this molecule? Okay. So what I'm actually doing is just solving for this one variable right here. Okay. So it's a really simple equation. So I just take divided by 4.8 divided by E is equal to the charge, right? Then I just plug in. This right here is always given in Debye. So if you have Debye, you know what the mu is. Okay? So if I take this now and I say, okay, let's take 2.4 over 4.8 divided by the distance. Remember, since we have the simplified equation, we can use the distance in angstroms as 1.23. If you crunch this number right here, you're going to come up with this delta value, or this charge distribution, as being about what? Anyone have their calculator crunch that number? I think it comes out about 0.4 is what I think I figured it out this morning. Is that what you come up with, about 0.4?